Hello, I'd like to welcome you to lecture 8 of 3N03. We'll start in this lecture to cover some interesting applications of diodes. We already presented the theory of the diode, PN junction, and we talked about the forward region of operation, the reverse region of operation, the breakdown region of operation. We have seen a number of examples. But now we'll start to move into discussion about some of the interesting applications of these diodes, including diode clippers, or they call them limiters, half-wave rectifiers, full-wave rectifiers, and the clampers. And we'll give a number of examples of that. All of us use all type of electronic devices, and these devices will take the outlet AC voltage and convert it to a DC voltage that we can use to supply our electronic circuits, like tablets, like cell phones, and so on. So inside every power supply that converts from AC to DC, you must have a rectification circuit, and the diode is a very important part of this rectification circuit. So as I explained, a rectifier is simply some sort of a diode circuit that converts an AC current into a DC current. AC current or AC voltage into a DC voltage. It converts a sinusoidal signal into some sort of pulsating DC voltage that can be even regulated and even smoothed out further. So here I'm showing you, this is what we have, say, in our from our AC outlets. It's 110 volts, 60 hertz, and this is what we get here from the outlet, and then you pass it through a rectifier, and this rectifier will rectify that, and then we create here a half-wave rectified out voltage, meaning that the negative voltage is simply trimmed out. So all the negative half cycles are trimmed out. So only positive voltage is allowed to go through. We call this one a DC voltage because if you connect a resistor across this voltage, the current will flow only in one direction because the voltage is positive. But of course, in order to be able to use it in powering, say, a tablet or a cell phone, or whatever the case may be, you must have other circuits that will smooth this one even further. For example, you can have a circuit that will smooth this voltage further, and then there are regulators and so on. So would there be other circuits that has to be used as well in addition to the rectifier? The simplest type of rectifier is called the half-wave rectifier, which is the one shown here. It simply clips, removes away the negative cycle of the sinusoidal signal, only allows only one half of the cycle in which the signal is positive to go through. A full-wave rectifier, on the other hand, will allow the whole signal to go through, but it will rectify the negative part. So here you can see we have this negative voltage. This negative voltage will be rectified to become a positive voltage. The circuit that does this, so you give it an AC signal and then it creates for you this rectified signal. And this signal, by the way, has double the input frequency, because this one here had a frequency of 60 hertz, so this was one complete periodic time, while for this one, this is a periodic time. The periodic time now is dropped by 1/2. So this one has double the signal, double the frequency. So the frequency for this one here is 120 hertz, say. So the good thing about this one is that we don't waste the negative voltage cycle. It's not wasted, is not clipped to zero. Rather, it's rectified, and then the whole voltage or current become in one direction. And of course, we have to go to make it to use other components to make it into a smooth DC voltage that does not change that much with time. Okay, we take a look at the very simple half-wave rectifier. A diode by itself is a half-wave rectifier. Why? If you see here, we have a diode in a circuit that contains an AC source and then it contains a load resistor. This diode, if you connect this AC voltage across it, it would allow current to go through only if it is forward biased. If the voltage across it is positive and exceeds the on voltage, which it can be zero, as we said in some diodes, say in germanium. In germanium, the on voltage is maybe 0.1 volts or 0.2 volts. For silicon diodes, the on voltage is 0.7 volts. Sometimes for simplification, we take it as zero. Okay, so here for this case, this is the input voltage, and only the positive part will go through if the value of the input voltage exceeds 0.7. So the output here, the diode will only allow the positive part to go through, and the maximum will not be exactly equal to the same as the input. It will be the maximum minus 0.7 because of the drop appearing across this diode. So this is a typical diode application. Now in the reverse cycle, in the second half of the cycle, where the input voltage is negative, so this means that this terminal is positive than this terminal. As I explained in the lecture, this voltage source trying to push current in the counterclockwise direction, but the diode does not allow such a current to go through. Then in that case, the diode will be open circuit, and this resistor is simply connected to ground and no current is going through it, and then the voltage across this resistor is simply equal to 0. So this circuit here is a typical half-wave rectifier. It allows only the positive cycle to go through, but it will deduct 0.7 volts from the whole profile because the drop across the resistor across the diode, and it will completely clip the negative cycle. The negative cycle does not go through because the diode in this case will be open circuit. So as we explained, a single diode rectifier will create an output waveform which looks something like this. It allows the DC part to go through, and then it will block completely the negative part. Only the positive half of the cycle will go through. The negative half is completely clipped, and this is how the output looks like. The peak voltage is not exactly the one that was applied to the circuit because the diode will deduct a little bit from that. So this is the original peak minus 0.7. Now I would like to see if when you get a signal like this one, you immediately ask what is the equivalent DC voltage. If we have the same DC voltage over the whole cycle, what is the value of that DC voltage? What is the value of this average voltage? It turned out that this DC voltage or the average voltage is simply the area under this cycle here, divided by the length of the total cycle. So this is what we do. We simply apply an average expression. We integrate over the whole cycle from 0 up to 2 pi, and then we divide over 2 pi. This is what's being done here, and this will give you the corresponding equivalent DC voltage. Of course, if you integrate something like this one, you integrate from 0 up to pi, and then from pi up to 2 pi, because it's not a single function. It's sinusoidal from 0 up to pi, and then it is 0 from 0 up to 2 pi. So this term will give us 0. When you integrate a sine, you get minus cosine. You substitute the upper limit minus the lower limit. Cosine of pi is minus 1. Cosine of 0 is 1. So you get here minus 1, minus 1. So you get here minus 2. Okay, and of course, you will still have this negative sign here. So this will give you 2, will cancel out with this 2. So you end up that your average is simply equal to the peak value divided by pi. Okay, so for a half-wave rectifier, the DC, the equivalent DC that you will get is simply equal to the peak value of the sinusoidal signal divided by pi. Okay, let's take a look at an example here. We have this resembles more like an actual circuit. We have here this side here we have oops, I keep on referring that. We have this transformer. We have a transformer here, and this transformer is connected from one side to the supply voltage, to the outlet voltage, which is 120 volts RMS, and this transformer here is 2 to 1. Why do you usually use a transformer? For stepping up or stepping down voltage. Usually inside every power supply that we have, there is a transformer that takes from 120 volts and then convert it to, say, 15 volts or 10 volts. So the reduction ratio can be way higher than 2 to 1. This one gives 120 volts RMS, and then the output here on this side is simply 60 volts RMS. And for all these transformers, I should mention, they have this notation. So if you have these two dots, this simply says that the phase of the signal across this primary winding is the same phase as this one across the secondary winding. Anyway, so you have an AC signal on this side, has a voltage of 120 volts. you have an AC signal across this side, which will have an amplitude of 60 volts RMS because of the reduction ratio 2 to 1. Now the diode, of course, will turn on during the one positive half of the cycle, and then it will turn off during the negative half. This is only a half-wave rectifier. So we'd like to determine the peak and the average power delivered to the load resistor. Of course, in this case, I can simply draw that the voltage delivered to the load looks something like this. It is 60 volts RMS, 60 volts RMS, while this part is simply being removed. So it looks something like this. Okay, so the other part here, the one here is can simply remove it. It does not show up. We have only the positive cycle going through, and then the negative clipped, and so on. So we'd like to determine what is the peak voltage. Let me correct this one again here. The peak voltage, the peak power is determined by the peak voltage. If we have, in this case, 60 volts RMS, and the on-diode voltage is 0, this means that the peak voltage appearing here will be 60 multiplied by square root 2 because of the RMS value. So this will give us the value of the peak power. The peak power is simply equal to the peak voltage squared divided by RL. So we know that the peak voltage is 60 multiplied by square root 2, and here you take the square root, the square of that, and then you divide by 220. Now, if you want to get the average power is related to the DC voltage. This is an alternating voltage. The one I'm showing you here is an alternating voltage. So if we replace this one by a DC value, and we already calculate this expression, we can determine what is the average power delivered. The average power delivered is this DC value squared divided by RL. So for the secondary winding, we know that the reduction, that the transformer has a ratio of 1/2. We have in the primary 120 volts. Then the RMS delivered to the secondary winding is 60 RMS. You multiply by 1.404, and this will give you the secondary voltage, which is 84.8. Now, the maximum voltage delivered to the load is simply equal to the peak voltage minus the on voltage squared divided by RL, because this is a voltage appearing across the resistor. It is the voltage of the secondary winding minus the drop across the diode. But for this one here, I'm assuming that the drop across the diode is 0. So it's going to be this number squared multiplied by 220. And if you calculate this one, you'll see that the maximum power can go up to 32.686 watts. This is the maximum power delivered. But of course, as we agree, the power is really oscillating with time, because the voltage across the resistor is simply going up to a peak, and then it is 0 during the negative part of the cycle. To determine the average power delivered to the load is related to the average voltage across the load. We agreed that the average voltage will be equal to the peak value divided by pi. We derive that together. So you square that, and then you divide by RL. So you have to divide this number here, the peak value, over 3.4, and I do not subtract V on here because V on is equal to 0. In other examples, if V on is 0.7, you have to subtract from this one the 0.7. Okay, so you square this number, you divide by 220, and you will see here that the average power is way less. It's only 3.31 watts. And the reason for that is that in this case, what is being delivered to the load is simply only the positive part of the cycle. So the average is less. It's the peak value divided by pi, and when you divide by pi, you are actually dividing the power by 9, or even above 9, because it is pi squared. The power is related to the voltage squared. So the power really gets significantly reduced by this division. Okay, well, the half-wave rectifier is not the end of the world. There are so many other rectifiers that are more efficient than the half-wave rectifier. The one that I want you to pay attention to is called the full-wave bridge rectifier. It's a very interesting one. And again, the way we have it, there is usually a transformer. It steps down from the 120 volts that we have from the outlet to, say, 15 volts or 10 volts. depending on what is the output voltage we are looking for. And then they create this bridge. This bridge consists of 4 diodes, and they are connected in this way: 2 pointing this way, 2 pointing that way. This is a common node here, and so this point here is the same as this point here. This has to be clear. This point here is the same as this point here. They are connected together, but in order to cross this other line, we simply draw them this way, and we take this as our ground. Now, the very interesting part about this structure, this transformer will scale down the voltage from 120 volts, say, to 15. During the positive part of the cycle, look what's happening. This side of the the secondary winding will have a positive voltage relative to this one. So this maybe relative this one here relative to this one will be positive. Okay? So this will allow current to flow in this direction and then to come back through this direction. And then the circuit is closed. In other words, D1 will be on. It will pass a current to this resistor. The current will come back again to here, and then it will pass a current through this resistor and then back to the negative terminal of the winding. Okay, the current will go this way during the positive half of the cycle. So if you have here, say, if the voltage here is 15, this diode is on, so the voltage here is 15 minus 0.7, and then the voltage here is 15 minus 0.7 minus the drop across this resistor. And the voltage here at this point is 15 minus 0.7 minus the voltage drop across the resistor minus another 0.7. Okay? Now, these two other diodes, D3 and D4, will be off at this stage. Why? Let's take a look. The negative terminal of this one connected to the peak voltage, but the positive terminal will be connected to a much less voltage. What is the voltage here? It is the peak minus 0.7 minus the drop across the resistor. So this takes us to this point. So this one is the peak, while this one is the peak minus 0.7 minus the voltage across the resistor. So this one is reverse biased. Okay, this one D3 is not on. What is about D4? D4, the cathode is connected to the peak value minus 0.7. What about the anode? The anode is connected to the peak value minus 0.7 minus the drop across this resistor minus the drop across this diode. So it is way less than this point. So this one is also reverse biased. So during the positive half of the cycle, only D1 and D2 are on. Here, so in this one here, in this part, I can simply draw it again. It is D1 and D4, D1 and D2 are only on. D3 and D4 are off. Okay, what's going to happen during the negative part of the cycle? During the negative part of the cycle, this terminal here, this side of the secondary winding, will have a higher voltage than this one. So this is positive, this is negative. Look how current will flow. Current will flow from here through D4, through the load resistor. It will come back through this node, and then through D3, and then to the positive winding. This is now negative, actually, in this case. So the voltage, look again how the current is going to flow. The current will flow from this now positive relative to this one. Current will flow from here through D4, through the load resistor, and it will come back through here, through D3, through the negative terminal. Okay? The very interesting part is that the current flowing through the load is flowing exactly in the same direction. So the voltage measured across the load will be always positive. So even though here the voltage is alternating direction, in the first cycle the current was flowing this way, then this is positive relative to this one. In the negative cycle, the current is flowing this way. Again, this is positive relative to this one. Then again, this is positive. So what is being seen in the outside across the load is something like this. It is simply a full rectification of the signal. And in the negative cycle, as I explained to you, current will flow this way through D4, through the resistor, coming back through D3 to the negative terminal. In that case, I will leave it for you to prove that in this case, D1 and D2 will be reverse biased, and they are off. Okay? So in one half of the cycle, D1 and D2 are on. In the second half of the cycle, D3 and D4 are on. And in all cases, the current flowing through the load is flowing in the same direction, and this is what results in this rectification. So the peak of the output voltage, as you could see, is equal, it's the peak of the secondary voltage minus 0.7, minus the drop across this diode. In order to find the average voltage resulting or corresponding to this sinusoidal voltage, and this is what we need, because this gives you the equivalent DC voltage delivered to the load, and from which you can get the equivalent DC current. You have to take the average over the complete cycle. Of course, if I can take the average only over 1/2 of the cycle, so I can integrate from 0 up to pi this sine waveform and then divide by pi. You can do that, or you can integrate from 0 up to 2 pi, and then you have to integrate over these 2 half cycles, so this will double the area. It's not that difficult to see that we have doubled the area that we had before for the half wave rectifier, and as a result the average voltage here is simply equal to the peak 2 multiplied by the peak divided by pi. Now the peak inverse voltage, as I mentioned to you maybe in the lecture, when a diode is reverse biased, so when you apply a very strong reverse biasing to the voltage, you don't want your diode to break, you don't want to enter into the breakdown. So when we pick these diodes that we use them for rectification, we have to make sure that the inverse voltage applied to them does not reach the breakdown voltage. It's very important that we do that. Usually the breakdown voltage for these diodes is way higher than the values used in this circuit. So if the secondary voltage is 15 volts, we use diodes whose breakdown voltage say equal to 30 volts. So we don't even have to worry about the breakdown voltage.